Solving exponential. We're going to be looking at a property that I introduced in an earlier video, and that is called the property of equality for exponential equations. When the base is the same on each side of the equal sign, then that means that we can equate the exponents and then proceed with solving if we have a variable to solve for in the exponent. So let's look at a problem. Solve the exponential equation using a common base. That means that we have to change the bases that we already have to make them the same. We're going to write the original equation and then change the bases to be identical. On the left-hand side, we have 1 over 2. To make that a base of 2, we're going to use the negative exponent property by taking the reciprocal and putting a negative 1 as the exponent. Notice how we keep that x plus 7 because it doesn't eliminate, it's still there. On the right hand side, we have a 4, and we're going to change that to be a base of 2 as well. 4 is the same as 2 squared. On each side of the equal sign, we have a power to a power property. When we have that power to a power, we multiply those together. So on the left-hand side, we're going to distribute, and on the right-hand side, we multiply. Now we have bases that are the same on each side, so that means that we can use that property of equality and get rid of the bases and equate the exponents. Now we're going to isolate our x's by collecting like terms. So I'm going to add x to each side, bringing my x's to the right-hand side, and divide by 7 to solve for x. We also have a similar property for logarithms. When we have a logarithm with the same base on each side of the equal sign, then we can get rid of the logarithm and the base and equate the two quantities that are left behind. In this problem, you'll notice that we have a base of 3 and a base of 5. We first start by trying to see if we can make these two numbers be the same using some sort of exponential property. Unfortunately, we're not able to do that. Therefore, we have to proceed with inserting logarithms. So we start by writing our original equation, and then we use the property of equality for logarithms by putting a logarithm on each side. This is the logarithm of base 10. You can't see the base there, so it's implied that it's a 10. Whatever we do to one side, we have to do to the other side. The next thing we're going to do, because ultimately we're trying to solve for x, is we're going to use the power property of logarithms. That's the property where we take the exponent and we bring that to the front of the logarithm as a multiplier. On the left-hand side, we distribute, so we multiply x times log 3 and 1 times log 3. On the right-hand side, it's already simplified. Then we're going to collect like terms. So we use x log 5. We subtract it from both sides to bring it to the left-hand side. And log 3, we subtract that from both sides and bring that to the right-hand side. In this same line, the left-hand side, we'd have also factored out an x because it's common in both terms. Remember, we're trying to solve for x, so we want to get to the point where we have a single x variable. Then we'll divide both sides by log 3 minus log 5, and on the right-hand side, we can take that expression and put it into our calculator and evaluate. So x is approximately equal to 2.15. Our next question is a modeling question. That means that we have to come up with the equation before we can solve it. The diagram shows how a forest fire grows over time. The fire department can contain a 160-acre fire without needing additional resources. About how many minutes does it take for the fire to become too big for the fire department to contain without additional resources? So it's telling us that there are 4 acres when time is equal to 0, 7.2 acres when time is equal to 1, 12.96 acres. So really these are x and y coordinates. So 0, 4, 1 and 7.2, 2 and 12.96. We have to model this exponential equation. So if we look at the x values, they're going up by 1. So let's identify what is happening to the y values. If we take 7.2 and divide by 4, we get approximately 1.8. If we take 12.96 and we divide 7.2, we also get approximately 1.8. What that means is that we have found a ratio for modeling our growth. Because the ratio of the number of acres from the diagram are all 1.8, the exponential growth model can use that b value as 1.8, where y represents the number of acres and a is the initial number of acres. So that's when time is equal to 0. B is our growth rate. So let's put all that information together into an equation. So the y value is 160 because that is the magic number that the fire department can handle without calling in additional resources. So we're trying to identify at what time would we have to go and pull in additional resources. So the 4 is our initial, and our b is that growth rate, which is 1.8. We're solving for t because we're trying to find the time it takes to get to 160 acres. So we start by dividing both sides by 4. Now to solve for t, we either have to make 40 the same as 1.8 or use our logarithm equality property. So we take the logarithm of both sides. We use our power property by taking that exponent and bringing that to the front of the logarithm, and then we divide both sides by log of 1.8. So our time is approximately 6.276 minutes. At that time in the forest fire, we would have to pull in additional resources.